right, just a couple of things first. First, sort of a good news, bad news situation here coming up. The bad news is there's no class on Monday. Monday's Labor Day. Sorry, the school's closed. We won't be here. But the good news is it won't affect us any because we meet Tuesday and Thursday. Good. So we won't miss a class. So I know y'all will be relieved to hear that. All right. Don't know of any other major things. Let's just go over basically where we are and where we'll be going from here. Today, we're going to continue in chapter 16. I think we have a fair chance of finishing 16. Believe a pretty good shot. We're only going for 2 hours, though. Well, I don't know. This is sort of a long chapter, so we may not make it. But anyway, we'll make a good stab at it. Then we'll be doing the lab for chapter 15, because we didn't finish in time last time to do the lab, so we'll be doing lab on 15. That'll be the next 2 hours, and the last 30 minutes will be the test on chapter 15. So where we'll be going next week, if we don't finish chapter 16 this week, we certainly will finish it on Tuesday, knock on wood, and then we'll have the lab for chapter 16. Also, we'll at least start the lab for chapter 16. Chapter 16 lab is going to be not one of the hardest labs or take the most time lab, but it's going to be the longest lab in the sense of this. It's going to take you minimum of 2 weeks to do it, maximum of a month, okay? I'll explain that when we get closer. What you're going to be doing is making observations of the moon over a 2-week period. But it has to be a 2-week period when the moon is up. So that will be something you'll be doing over a period of time. So we'll get started on the lab, get the first part of it done in class, but then the last part you'll be doing at home. And we'll talk about that Tuesday. Okay. Any questions on what we've done so far? Specifically chapter 15, which we'll have your test today. We'll do the lab and the test, or anything we've done in 15 so far. Well, let me say this too. Sorry about this one. I've made some progress on getting your labs, the first lab, graded. Okay? I have had so many impediments and things getting in the way, like this morning. I had to make a phone call in my office hours this morning. I tried to make it. Had to leave a message. So later I tried again. Left another message. Later I tried again. I don't think the guy ever answers his phone. So that was one. Also, I had to set up for some of my classes what the WebAssign codes and stuff like that so they could get in Cengage books. And the email took long enough, but then I had to follow it up with a phone call because I didn't know the guy was still working there. And sure enough, he was, but then he had questions, and he wanted to send an email somewhere else and stuff. Then I had to respond to that one. And soon I was in an email vortex, and I couldn't get out. And so when I thought, well, it's time for me to eat lunch. Well, no, I thought, it's time for me to run off the test, so then I'll have time for lunch. I looked at the clock, and I was 5 minutes late to that class. What I thought was before 11, it was after 11:35. So I went, yeah. So it's just been that kind of day since then. I did get most of my lunch eaten in the last half hour, but whew, it's been crazy. So anyway, I'm behind in grading already this early in the term, and that's never a good sign. But I think I have 3 hours of office hours tomorrow. I know I lose one because the dean has called a meeting on Friday afternoon, the Friday before a holiday weekend. Isn't that special? Okay. So anyway, I hope in the first 3 hours to be able to get some grading done, maybe even caught up. But we have another lab today and another test today, so whether I'll make it or not, I don't know. I'm going to maybe be praying for rain this weekend so I can get some grading done and won't be working outside the whole time. So I enjoy working outside. All right. Any questions? All right, we left off last time. We were looking at various motions of the Earth, and the strangest, the slowest, the one we never notice, is called precession. Now, precession is, the definition is the very, very, very slow wobble of the Earth's rotation axis. I mean, this is incredibly slow. It's actually a reaction to the Earth, to the gravitational pull on its equatorial bulge by the moon and the sun. Because our moon is so big and so close, it yanks on us. We talked about how our center of mass, does that. But also, the sun is really big too, further away but still pulling on us, and this makes us wobble a little bit in our spin. Okay, so that's what's happening. Now, when I said how slow it was, 26,000 years for it to go around one circle of its precession. Not going to bother me yet, okay? I'm not going to be around in 26,000 years. But what that means in those 26,000 years, if we haven't blown up the planet or something, then we'll be back with the North Star as our North Star. Because after that, we're going to drift away, or after now, we're going to drift away, and we won't be pointing anywhere for a while, and then we'll get a few other stars, and in 26,000 years, we'll be back pointing toward the North Star again. In all of recorded history of sailors and everything else, our North Star has been our North Star. But they've traced back and seen that sometime in the far distant past, not when anyone was here to notice it, it was not the North Star. Okay. Now, the changes in the direction of rotation axis, this changes the direction of our rotation axis on the celestial sphere. And Polaris, what we now call our pole star, was not always our North Star, and the position of the equinoxes in the zodiac changes. Because if you think about it, if our North Star, if we're wiggling from that, that means our whole celestial equator is wiggling, which means our ecliptic is changing, okay? Slightly. Now this they can notice, because that's a bigger deviation than just pointing at a star, and a few of the constellations on the ecliptic, are not really on the ecliptic anymore. So but they're not going to go and change the zodiac sign. So I think all the people who like to read those, they're going to stay the same. Okay? Here's kind of what it's like. Do any of you even recognize that toy? A top. Okay? And y'all know how it works. You wrap the string around, you throw it, and if you're good at it and stuff, it spins. It spins almost directly upright. But every now and then you'll see it start doing this. That's called precession. And that's what we do. It's a very slow, spinning like crazy. Our rotation is spinning like crazy, but the actual axis rotates a little bit. Very slow. Nothing this big. Nothing anywhere close to that much. Okay? Now, this shows us, and this is 26,000 years around this thing, but up ahead, about 14,000, I'm not sure we'll still be here then, but if we are, Vega will be our North Star. Okay? So that's more than halfway around the rotation. And Vega is a much brighter star than our North Star today. There could be some other little stars in here that we'll pick up in between, but that's going to be our next major one. So that's going to be 14,000 years, 12,000 years from now, okay, approximately. Okay, we'll be over that way. All right. Nothing to worry about, okay? Don't write home, okay, never mind. Now, 16.3, place and time. Too bad we didn't get that done last time, but here we go. Earth's periodic motions provide the basis for determining place and time. Time makes great sense. In a sense, so does the place, but it's a little more abstract than the time. All right, the rotation provides an axis of rotation useful in determining locations on the globe. Okay, let me get my good old trusty visual aid. What's one obvious thing that the rotation of the Earth defines for us? What? Okay, as soon as it's going to do that, that's going to be the time part of it. But as far as place, location, what does our axis define for us right off the bat? What? Absolutely, north and south poles. They are where the axis comes out here and goes out there. Okay, the poles are defined by our axis of rotation. North pole at one end, south pole at the other end. And then what other thing is defined by those two poles? Okay, you're getting at it. What's that?
Hemispheres.
Okay, yes, it breaks the Earth into two hemispheres. And what joins those two hemispheres? The equator. It defines exactly where the equator is. Okay? And then I heard you say latitude and longitude, right? That's exactly how, and all that is based, well, number one, on the poles and the equator. Okay? And you have to do some other manipulating around, but that's helps us to find place on the globe. The rotation and the revolution determines the cycles which can be used for time standards. And that's what you talk about, the seasons, and that type of stuff. All right. So place and time are determined here. So let's start with the place part. Now, if we lived on the flat Earth like people used to think we did, you could define any place on that thing by two coordinates, okay? How far you are left or right from the center, whatever you determine the center to be, how far up or down from the center. Two coordinates, play. Pretty easy to do. Intersection of two straight lines won't work on the Earth's surface because we live on a sphere or something pretty close to a sphere. So we can't have XY coordinates that give us what we need to know. For instance, in our book, if we knew that you were on a certain page and the word or letter or secret message that you were looking for was so far from the center of the book and so far down from the top of the book, you know exactly where it was. Well, there's not exactly a top of the globe and there's not exactly a center of the globe. In a sense, there really is, but that doesn't tell you place, okay? Exactly. And this is Maurice, right? Okay. All right. Is anyone else coming in since I called roll? Okay. We're sitting on here with your choice. Okay. So if you had a flat Earth, it'd be really easy to identify place. 2 points. Left, right, up, down, whatever. On a globe, however, on a sphere, you need something else. And since we have identified the poles, north and south pole, where the axis is, axis of rotation, that gave it to us, and then the equator, then you can imagine cutting a circle, and someone mentioned the hemispheres, cutting that into and putting a compass, a protractor in that and measuring the angle north and south. If you went from the center of the Earth, sort of like the center of the page, center of the Earth, and then measure the angle. And this gives you what they call the parallels, which another name for it is the latitude lines. And this is showing 20, 40, 60, 80, and of course 90 is at the top. And that's to the north. You can do the same to the south, 20, 40, 60, 80, and 90 at the south pole as well. These are called the parallels because they're all parallel to one another. Okay? They're circles. Only the equator is what we call a great circle that goes through the center of the Earth. All the rest of them are smaller circles that you get right near the poles, and they're really tiny circles. Okay? Poles themselves are not circles, they're just points. Okay? So this is one way, this is the first step toward identifying place. Okay? The poles give us the ends, the equator is midway between the two, and then measuring the angle from the equator to the pole. That gives you your parallels or your latitude lines. Okay. Now, let me pause a moment here. This chapter, the lab is going to relate very closely to what we study in the chapter. Next chapter it will too. Okay? But then coming up a few chapters from now, there's some things like plate tectonics. You can't really build an earth and make plates that move around and cause volcanoes and stuff. I wouldn't want to put that in the hands of students anyway. No, I wouldn't say that. Did I? Okay, so after a while, we'll just be doing sort of random labs. And one of those random labs, sort of random, but not really random, will be in a chapter that doesn't have anything else at work. So we'll be doing latitude and longitude. So we'll be coming back and doing this kind of thing in a lab. Far removed from now, okay? But it works for physical science anyway. You know, it's just one of those labs, okay? So this is what I was talking about. If you were to make a cutaway view and measure the angle from the equator, the equatorial plane here on the hemisphere, up to these various lines, that gives you your 40, 60, 20, 40, 60, 90. I left off the 80 on this one. Okay? If I were doing this, I would have done it by 15. So I've done 15, 30, 45, 60, 75, and 90. But they didn't do it right that way. That's why I don't write books, I guess. Okay. So anyway, that gives you your latitude lines. Whatever, they're called the parallels, I'm giving it the name the latitude lines. Okay. Now, this gets a little rougher. Just like when we were trying to define right ascension, we had to pick some arbitrary point to go from. We went from the where the vernal equinox crossed where the celestial equator crossed the ecliptic at the vernal equinox, and we measured right ascension from there. You had to pick some point to measure from. Okay, when you're going left to right, okay, around the globe, there's no starting point. So they arbitrarily picked one. Okay? And that arbitrary choice, I think I mentioned this before, who was the queen of the oceans? Before we? Second? England, yes, the queen of the oceans. Okay? And her Royal Naval Observatory, which is where the Royal Naval things were headquartered, was a little bit east of London. And they just arbitrarily chose that to be the line that goes from the North Pole through the South Pole, that great circle that connects those two, that goes through London, England's meridian, local meridian. They named that the prime, meaning first, meridian. Except it's not really 1, it's 0, okay? 0 degrees. And then from there, we measure east 180 degrees and west 180 degrees. Until we meet back here on the opposite side, and there's another special line over there, okay? So here it's showing east, there's east 90, east 120, east 180. Usually just 180, you just call it that. Or you can measure the same west. Now this looks like, that's 90. Goodness, this is hard to see. 1, 2, 3, 4, 5, 6. So, yeah, they're 15 each. 15, 30, 45, 60, 75, and 90. Okay, and this would be 15 west, 30 west, and the rest of it's on the back side. So that's how we choose our east-west location. North-south, north and south of the equator, goes from 0 to 90 north, 0 to 90 south. That gives you the parallel. And now we've got the longitude lines, which are east and west of the prime meridian. It goes through London, or near London, England. It goes through the Naval Observatory. I think I told you about my wife being there between exits. Yeah, okay. All right. Now, I see nothing there, okay? What's that? Somebody what?
Somebody came in.
Oh, really? I didn't mark the roll. Who was it came in? Oh, got you. Tegan. I should have called you. Okay. Good deal. Thank you. Okay. All right. This is what we were talking about before. So our position on Earth, where are we on the globe? It's the intersection of some parallel and some meridian. Just like east, west, north, south, x, y, whatever, on a flat plane, parallels and meridian, that defines where we are. With respect to the rotation axis, now the parallels are your latitude measurements, the meridians are your longitude. Let's think about meridian. Every meridian line is a great circle because it goes from North Pole to South Pole. So they're really close together near the poles and pretty far apart near the equator. Okay? And that's how we identify location on the Earth. Parallels to latitude definitely come straight from the rotation axis. With meridians, you had to arbitrarily pick a meridian. Okay? And that was the prime meridian. Now this is showing the same thing over again. I don't know why. The parallels measured in degrees north or south of the equator being 0 degrees north or south, and then so many degrees north, so many degrees south. And there, show that picture again. I don't know why, but we've seen it before. There it is again. Okay, the longitude lines are measured east and west of the prime meridian. Prime meridian counted as 0, but they go 180 east, 180 west. Okay, latitudes 90 north, 90 south. Okay, now, and there's the cutaway view of the longitude lines again, the angles. And do they do one more? No, they've already shown them twice. Now, they're going, in identifying place, there are some special latitudes, okay, parallels, and there are some special, or at least one special, meridian that we'll talk about, okay? I think this is the place they talk about it. It should be. Yeah, it's going to be a little bit before. Yeah, it's when we start talking about time. Okay. So we'll get to the special meridian later. But several special parallels or latitude lines, they say are climate related. I would say the climate is related to them rather than being related to the climate. Though I guess you could say it both ways. Can anyone think of what those special ones are? We've already mentioned, I think, every one of them. What are they?
Is it the tropic of Capricorn?
Okay, we've got our two tropics. In the northern hemisphere, how many degrees above the equator? 23.5 degrees above the equator is another parallel, named the Tropic of Cancer. And south of the equator, another 23.5 degrees, that's your Tropic of Capricorn. Okay. Now those are circles, parallels, okay? And what do they represent? Yeah, that's the tropics, and that's why they say climate related, because they're always warm, usually moist, okay, that kind of stuff is there. But what is it that determined there would be 23.5 degrees north? Or south? Say again?
The equator.
From the equator, yeah. What determined that?
The sun goes directly overhead.
What?
The sun goes directly.
Okay, you got it. The sun is directly overhead at any day, any time, somewhere in those tropics. Directly overhead. Never directly overhead north of the Tropic of Cancer, never directly overhead south of the Tropic of Capricorn. Never. The sun stays in a band between the tropics, directly overhead at noon. Okay? So that's what defines the tropics, the Tropic of Cancer and the Tropic of Capricorn. Okay? So you've got two of them. There are two more. Okay? Anyone think of what those two are?
Arctic Circle.
The Arctic Circle, and then there's a corresponding Antarctic Circle. Now, what do those represent? Way up there, or way down there. Second. Okay, it's north and south. And what is it that... Okay, how far north and south? That may be a good question.
66.5.
Second.
66.5.
Okay, 66.5 degrees. How did you get that?
From the 23.5 to 90.
Subtract the 23.5 from 90. So these are 23.5 degrees from the North Pole, or 23.5 degrees from the South Pole. Well, what makes those special? Those circles. Arctic Circle, Antarctic Circle. Above that, above the Arctic Circle, and on the Arctic Circle, there's at least one day a year when the sun never sets and when the sun never rises. Okay? Because of the tilt of the earth, you're going to be right in the sun today. Let's do it like this. Do you ever see the North Pole here? That's been like this. No, you don't. But you see the South Pole, it never goes away. 24 hours of daylight there, 24 hours of darkness here. This day, same thing from the north, but not the okay. So anywhere above the Arctic Circle, 66.5 degrees north, and below the Antarctic Circle, 63.5 degrees south, you'll have total darkness, 24 hours for at least one day. The closer you are to the poles, the more days you have of that, but on the circle. Whereas down here, 24 hours of daylight. Up here, 24 hours of daylight. Over here, 24 hours of darkness. Okay? 23.5 degrees from the North Pole. Subtract 23.5 from 90, and you get 66.5. Whereas the tropics, the sun is coming in directly on summer solstice, right there at the Tropic of Cancer. It's directly overhead, and on the winter solstice, well, our winter solstice is directly overhead the Tropic of Capricorn. Okay? And so those are the other two. So those are the special parallels. The equator, the tropics, and the Arctic and Antarctic circles. Okay? All depend, except for the equator, on that 23.5 degree tilt that we have. There. All there. Summer solstice when we're tilted to the North Pole as far to the sun as it will be. Winter solstice when the South Pole is tilted as much to the sun as possible. North Pole tilted as far away. All right. Now, what does that do with climate? Very warm in the tropics, very cold in the Arctics and Antarctic, inside those circles, or outside those circles. Temperate in between. Now, the temperate's a really big region. Can be semi-tropical down here and almost Arctic up here. Okay, so still very much variation, but you will always have some daylight up here. You'll never have the sun directly overhead in here. Okay, so it's a mix between the two. We live where? temperate. We're not in the tropics. We're not in the Arctics. Okay. All right, now let's get around to time, which is also related to that. The time standards depend on measuring intervals between evenly spaced periodic events. Okay? Now, that's a pretty nebulous kind of statement there, but it is absolutely true. Now, astronomical examples, the rotation of the Earth on its axis, that's once every, how often? One spin? 24 hours, okay? Revolution of the Earth around the Sun, 365 and a fraction days, okay? And the combination of those with our tilt, with our solstices, with our equinoxes, that gives it, well, the rotation basis for the day. Now, we haven't said anything about gives us the months yet. What do you think our months depend on?
The seasons.
To say again?
The seasons.
Okay, sort of, but more specifically, what word do you almost see there, missing one letter? Moon, exactly. The months are based on a lunar cycle. So this isn't quite what we're talking about, rotation of the Earth or revolution of the Earth. The months are more based on the moon. But when the months are is our seasons. The seasons, those are between the equinoxes and the solstices. Okay? So that defines our seasons, and that all depends on the tilt of the Earth and our trip around the sun. The year, then, of course, is one revolution of the Earth around the sun. Now, there are different ways to measure days, months, and years. That's part of what today's, even though it's the lab, mostly based on last chapter, it'll be in this chapter's. The stuff we're doing now will be in last chapter's lab. Okay. Again, the labs don't match chapter by chapter exactly. The first three come close, and the fourth one comes really close, but many of the others don't pertain directly. Okay? So let's look at daily time. Okay, Earth-Sun motion. If you're somewhere out there in space looking down on our North Pole, we see that the Earth revolves counterclockwise. So if you were looking there, the Earth revolves counterclockwise, right? All right, going counterclockwise. Okay, I'm sorry. I was doing the spin. It also goes counterclockwise. If you're looking down from here, okay, we're also going counterclockwise around the sun. That's what we're talking about here. So counterclockwise around the sun and rotates in the same direction counterclockwise. So I got the second one first. Okay, now if you're on Earth, you don't feel us moving any, do you? You don't feel us moving around the sun. You sure don't feel us spinning any. It looks like the sun rises in the east and sets in the west, approximately anyway. Okay? You know it really doesn't. Well, it does rise and set, but it's not because it's moving, it's because we're moving. All right? Now, here's another thing that causes a problem. When we move from here one day, okay, because we're moving around the sun at the same time we're spinning. Now, we don't move. We may move that far, but the angles are really deceiving here. We are way long distance from the sun, so it makes a really small angle, but it's a pretty decent distance, okay? Now, here's the problem. If the sun is rising, if it's noon, let's say it's noon, right there, okay? Now, we're going to spin one time around, and we spin one time around, we're right here. But the sun is down here. So, it's not noon yet. We need to go a little bit further for us to get to noon again. Because noon is defined to be when the sun crosses our local meridian. And because in that day, that it took us to spin once, we also moved a little bit this way, so we had to go just a little bit further around. So it's not, one day is not one spin of our axis. One day is when this goes from the sun being directly overhead at this time to the next time, we spun one time around plus a little bit more. Okay? So that's why there are two types of days. And we'll talk about that actually in today's lab too. So, and we'll go through some of this all over again. So, here's what I just was saying. Noon is technically the time at which the sun is crosses our celestial meridian. If this is our celestial meridian right here, when the sun crossed it, and that was a little while back, that was our local noon, that day. Okay? The apparent local noon, and when we were in the Navy, we called this the local apparent noon, L-A-N, but they call it apparent local noon, is at a particular longitude. Now, very seldom does it cross exactly, do we say that's 12 o'clock. We have to be just the right place at just the right time for that to happen. Okay? Now, our apparent local solar time is given by the position of the sun in the sky. Okay? And that's actually how they used to measure the first clocks. And what was that called? Sundial, exactly. Another name for sundial is a gnomon, and that must be Greek or Latin or something. It's certainly not any language I recognize. G-N-O-N-O-N. Gnomon. Gnomon, yeah. Okay, another word for sundial. And actually, we're going to learn another word for sundial, and that will be part of today's lab too. I think we're going to get to it in class first, but we'll get there. Okay? That's not the time shown on clocks. What the sundial did, you set it up so it faces pretty much due north, and where the shadow is at any time of day, that estimates what time it is. When does it not work well? At night. Okay? There is no shadow at night. And cloudy days are also an issue. Okay? So rainy days, really bad. Okay? So you can't always tell. But that's not the important thing. It's still not the time shown on clocks because the clocks are based on something else, another convention. Somewhere it's correct, okay, but it's not always. Now, a term called mean solar time. That's the time average from the apparent solar time over 365 days or something like that. That's what we call mean solar time. Average over two effects. Number one is the Earth's orbital speed. Remember, we are a little bit closer to the sun about what time of year? In January. And a little bit further from the sun in July. Okay? Now, when we're closer to the sun, that means we're moving a little faster. Okay? We got another chair for you there. But, huh? Well, if you want to turn a desk, what happened to the chair? Okay. If you want to turn a desk, you can still use the chair. Oh, we got a spare desk. Well, whatever. You want to?
Yeah.
Okay.
I do.
I got two chairs out for y'all to use. That's why I get up and move around a lot, because I don't like sitting for 2.5, 4.5, whatever hours, okay? Just way too much. Okay. All right, so mean solar time is the time average for apparent, because guess what? When we're closest to the sun, we're moving a little bit faster, so our noons come a little bit more frequently. When we're further from the sun, it takes a little bit longer, because we're moving more slowly around there, okay? So our noons are a little bit, our actual noons, the apparent local noon, are a little bit further, so we average. So that's one way, because our orbital speed changes through the elliptical orbit. And then the other issue is the equator is inclined to the ecliptic. The equator is inclined to the ecliptic, so that creates another little variation. Not a huge amount, but some. So what's our mean solar day? We say it's 24 hours. That's the average from our mean solar times. 24 hours, we count that as a day. Even though it won't be crossing our meridian exactly 24 hours apart. Sometimes more rapidly, sometimes less. Okay. So that's problems with our days. So what is a day? A day could be the length of time required for the Earth to rotate once on its axis. That kind of day is called a sidereal day. Now, when you see the term sidereal, think stars. Okay? Because the stars are so far out there, they're basically fixed in place. And if you measured the time, you're going to do this at night, at the time this star crossed the North Star, it's always up, right? When it crossed your local meridian and did it day after day, that's going to be it. It's not going to be the same as the solar day, because the solar day, when the sun crosses your meridian, you've gone a little bit further. Solar days are longer than sidereal days. Sidereal day is the interval between two consecutive crossings of a celestial meridian by a particular star, not our sun. Our sun is a star, some other star. Okay? Little variation because of the Earth's constant rotational rate. There's nothing to change. It doesn't matter about our tilt or our speed around the sun or anything. That's going to be very, very constant. Okay? That's a sidereal day based on the star. Based on our sun, though, is the interval between two consecutive crossings of the celestial meridian by our sun. Now, the reason of the difference here, the revolution about the sun changes the Earth-Sun orientation every day. And how much does it change? About 4 minutes. And we'll do that in the lab today. About 4 minutes longer than the sidereal day, your solar day is. Now, I think this belongs on this side, okay? The sidereal day, this belongs over there, is 23 hours, 56 minutes, 4 seconds, okay? Almost 4 minutes, okay? This one is 24 hours. We've done that and set it up so that is exactly 24 hours. So this bullet here belongs over on that side. Okay, sorry about that. The graphics person botched it just a little bit. All right, now, there's another issue here. This thing is called the equation of time. Now, when I see or read a word like this, I expect to find an equal sign somewhere in there. This is not that kind of equation, okay? But this traces the yearly variations between apparent local time and the mean solar time. Okay? Because we do have those variations. We're going faster sometimes, slower at other times, tilting, all that kind of stuff. It does create some variations. Now, I don't know if you've ever seen a globe that had one of these on it. I know the one that we used to have at our home when I was growing up had one, but I never knew what it was. It had this thing that looked like a figure 8 on it. Have you ever seen a globe that had that? Usually right out in the middle of the Pacific, because it's not getting in anybody's way out there. That's what we're talking about here. Now, we could, if y'all hung around long enough, like a whole year, we could do this. Okay? What we would have to do is block out all the light from the room, except, say, a little pinhole. Now, you might want to take out that maple tree, too. That makes it a little easier to do. And if every day at noon, you mark where the light came through that little hole in the black plastic that you put over there, mark on the floor where that light shone. Exactly at our local noon. Not at noon clock time, exactly at our local noon. Mark on the floor where the sun shone in through that hole. we form a little figure 8 on the floor. Okay? That's what they mean. Appears as a figure 8 on the floor. The two effects, one is the axis tilt, that's the north-south motion, that depends on how long that figure 8 is, up and down. And then the orbital speed, that gives the deviation, that gives the width of the 8. Okay? So the length of the 8 is by the axis tilt, and the width of the 8 is orbital speed. Now, when you put all that together, that's what they call the equation of time. Okay? Now, in your text, let me see if it's in the slide too. Okay. By the way, we're over about, and you may find these exercises, examples interesting. You may or may not. I'm going to go back to one. This one, okay? Remember I was saying we have a little variation between solar day and sidereal day. So sidereal day being the star-based and solar the sun-based, because we have to turn a little bit further because we're going around the sun. So therefore, when you add all those little additions up, guess what? You have one more spin. So a sidereal day will have, so sidereal year will have one more sidereal day than a solar year will have, only we don't call them solar years. So we'll get to that a little bit later, but I thought since I had it there.
A sidereal year will have what?
One more day in it than a solar day, a solar year, though we don't call it solar year. We'll get to that a little bit later. I'm sorry I jumped the gun on that one. Okay. Now, this is a true picture, but it really has nothing to do with the figure 8. I've tried like crazy to think, well, if you flip this over, you sort of form a figure 8, but this really isn't what it's talking about. This is just the path of the sun, and you see this would be on a vernal equinox. The sun is directly over the equator. At summer solstice, it'll be directly over the Tropic of Cancer. Fall or autumnal equinox, back over the equator again. And then the winter solstice, so it's not winter down here, that would be directly over the Tropic of Capricorn. And then you go back up and it crosses the equator. This point and this point are exactly the same points. They did a little bit more here, just so they could get Siberia together there. You see this part sticking up here. Okay. So anyway, that has nothing or very little to do with our figure 8. It kind of looks like it would be, but I haven't figured out any way to make it relate. It's just a nice picture and it's showing something true, but it's not what we were talking about. Okay. But anyway, I was going to say these examples that you see on page 417, they have you calculating how many sidereal days are in 1 year, blah, blah, blah. So what is the age of a 20-year-old person in mean solar days or in sidereal days? Yeah, really useful stuff to know. Okay. So anyway. This one, though, this does reveal our figure 8. Okay? Doesn't look like it, but it is. In your text, if you, on page 418, you'll see that sunspot, you might say, traced on the floor, but it takes a whole year to draw the entire figure 8. Now what you do here with this one is fold it right here. Fold this half over this half, and then you have your figure 8. Okay? So this is related to the equation of time, that figure 8. handle life of figure of 8. Now this is indicating, because the winter solstice is, see, this is middle of December. I don't know, they don't have this. This is end of December here. So that's the 21st of December. No, that's not quite right either. Anyway, but this part here connects to that part there. So you could, if you fold it right in the middle here, then these would connect exactly. Okay. Now, of course, people at home can't see what I was just doing, but sorry about that. You should be here. Okay, never mind. Okay. All right. Before we get too far here, keep looking for this other place where they use the same word, and I just don't see it here. Let me see if it's showing up. It's not. It's in the lab. That's where it is. Okay. This equation of time, I thought it was in the text. It used to be in an earlier edition, but now it's in the lab. This shape, that figure 8, is called, now maybe it is in here, I just haven't been able to find it. It's called the analemma. A-N-A-L-E-M-M-A. Analemma. A-N-A-L-E-M-M-A. Okay? And it'll show up on the lab today. Okay. Now, it used to be in the text, and it may still be in here, but I just haven't seen it yet. Let me go to the back and see if it's there. No, don't see it here either. Okay. A-N-A-L-E-M-M-A. Analemma. What's that? No, one word. A-N-A-L-E-M-M-A. Now, the interesting thing about that word, and it'll be in your lab today, is that also means sundial. Okay? So a sundial is that thing like this, a gnomon, and it's also the analemma, which is a shape. And they're not really all that closely related, but they are sort of. Okay. Now, before we go any further, and we're going to talk about this in a slide or two, they talk about daylight saving time, which is not particularly one of my favorite subjects. Okay? Are you really saving any time? Or saving any daylight? Not really. Okay? Huh?
Just moving it.
What's that?
Just moving it around.
Moving it around. That's all you're doing. Now, I've always blamed it on the bankers, that they want to get out early so they can hit the golf course and be able to play 18 holes. Did I really say that out loud? Or the executives or whatever. Of course, they blame it on the farmers, that the farmers want that extra hour of daylight. But guess what? The farmers get up with the chickens and they go to bed with, they are out there the whole time. So it doesn't matter any to them, except for this. We live next door to a neighbor. I grew up on a farm. The farm just east of us was a dairy. And when they went to daylight, when they were on regular time, usually those guys had to get up, the dairymen had to get up about 4 in the morning to start the process to milk the cows in the morning. They had to do it all again in the afternoon. When we went to daylight saving time, they had to get up at 3 o'clock in the morning because the cows didn't know it was daylight saving time. Their bags were full and they wanted to be milked. So I don't think it was the farmer's fault. That was the bankers. Never mind. Okay. So anyway, they do have a little blurb there. There are questions to discuss. If you want to write on that, that is a reasonable paper topic. Okay. So anyway, the equation of time, and that's what a lot of today's lab is going to be based on this. Even though today's lab was supposed to be in the last chapter, it will be doing it in today's lab. Okay. Now, let's look at these time zones. That's sort of what we're talking about when we're talking about daylight saving times and other things. Okay? How far it is around the globe? Oh, did I ever mark Lexi here? I saw her come in. Yes, I got you. Okay. How many degrees it is around the globe? 360 degrees of longitude, okay? And all around the globe, at any point around the globe, it's a different time, really, isn't it? Okay? Some places, if the sun's just noon, at noon, while on the opposite side, it's midnight. Over here, it's morning. Over here, it's evening. Okay? So, it's at any given time, it's up. So, the globe represents 24 hours. And if you divide 24 into 360, you'll find out that 15 degrees is an hourly time zone. Because we don't go by local apparent noon, otherwise it would be a little bit different time here than it would be in Birmingham, quite a bit different from Tuscaloosa, and way different. Yeah, okay. You just couldn't do that. Okay? So, we just split the globe approximately into 15 degree time zones. Now, Greenwich Mean Time is 15 degrees around the prime meridian, which means 7.5 degrees east to 7.5 degrees west. So they're centered on the middle one, not on the other. So that would be Greenwich Mean Time. This would be +1, +2, +3, +4, +5, and we live in our Eastern Time Zone is +6. Centered on, oh, that's Central Time Zone. Okay. Central Time Zone is centered on 90 degrees west. We're a little bit east of that. We're in that time zone. Okay? So they're all about 15 degrees apart. Now, they do some adjusting, they say, for local consistency. And here's what they mean by that. The actual split would be something about here to there. And that, now, here's a problem with taking a spherical globe and trying to draw a map that's planar. It just doesn't line up properly because things should be getting closer together at the top and wider at the bottom. You just can't show that on a rectangular plot. So this line technically should connect with there. But you see, in reality, it doesn't. Okay? Poor old Tennessee being such a long state, east to west, the eastern tip is in is that time zone? I used to live in it. Eastern, yeah, Eastern. I was thinking Atlantic Coast Conference. Okay. Eastern Time Zone, Central Time Zone, Mountain Time Zone, Pacific Time Zone. So I was thinking Atlantic here, Pacific, but that's Pacific. This is Eastern. Now, Maine should be, this part of Maine, half of Maine should be in the Atlantic Time Zone. That's what the one out here is called. But we wanted to keep it in the rest of the Central, so we adjusted that for a local consistency. Okay? Now, poor old Tennessee, to be locally consistent, you can't do it. So Eastern Tennessee is Eastern Time Zone, Western Tennessee is Central Time Zone, right where we are. Okay? So Chattanooga, I think, is Eastern Time Zone. Nashville and Memphis are Central Time Zone. Same thing with Kentucky. I can't picture exactly where Richmond, Kentucky, I'm pretty sure is over here. That's Eastern Kentucky University, whereas Western Kentucky University would be over there. So I know those two would be different. But the capital, Lexington, and Louisville and stuff, they have to do some jiggling. Indiana, another strange one. This part of Indiana is central, but this part is not. But this part is central again. Now, why is that? Well, what's the big city here in Illinois? Chicago. And a lot of people from around Chicago, even if they live in Indiana and possibly even in Michigan, they may work, if not in Chicago, with something close enough to Chicago that they want us to be on the same time zone. Believe it or not, we do something like that down here, or at least I've heard this.
Yeah.
Anyone from anywhere around Phoenix City?
Yeah, like Nick, fit and everything down Georgia time. It's like Valley down Georgia time. It's Alabama, but it's still Georgia time.
Okay, and why is that? What's right across the river? Near Columbus, Georgia, and also near Fort Benning. Big draw there. So they decided, since their whole economy and everything else is based more around Columbus and Fort Benning than it is anything in Alabama, they go on Georgia time. So you're absolutely right. Okay? I thought I was going to surprise you with that, but you got it. Okay? Now, other variations here. Now this is, I heard something recently about this, and it's sort of bizarre, but the upper peninsula of Minnesota, it looks like that should belong to Wisconsin, doesn't it? And that was all a political boondoggle, you know, somewhere way in the past, like everything squirrely is political at base, I think, anyway. So anyway, but this is Minnesota, so they stay on Eastern time because most of Michigan. Minnesota's over here. Michigan, and this is called the Upper Peninsula of Michigan, but it's not connected to the rest of Michigan. It's connected to Wisconsin, but they stay on, because Michigan is on Eastern time, even the Upper Peninsula stays on Eastern time. So that's what it means, adjusted for local consistency. Whereas this little tip of Minnesota looks like maybe it could have been, no, they keep it on Central. Okay. That's what they mean, local consistency. The panhandle of Florida, that's right under Alabama, that's Central time, but all the rest of Florida is Eastern time. Okay? Down here, south of New Mexico, this little bit of Texas here is Mountain time. All the rest of it is Central time. Why do you reckon that? Now, if you've ever driven through West Texas, I did once, and I swore my car was up on jacks because the horizon never changed. You know, it just felt like I was up there spinning my wheels because it always looked the same. For days, it looked the same, or it wasn't quite that long. But, there's not much out here. The nearest town to this part of Texas is Santa Fe, New Mexico. Not anything in Texas. So they get on New Mexico time, so Mountain time. And somewhere here, Nebraska here, there are big population centers, for Nebraska anyway, Omaha and Lincoln, both over here. West part of the state, there's not a whole lot there. I mean, quite a few people live there. But where do they go? Denver. That's where they go to do their shopping. They don't drive all the way across here. They just go down to Denver. So that part of the state is Mountain time. Same thing with, I don't even know what's up here. I mean, South Dakota, what's in Wyoming? Nah, I shouldn't be saying that. You know, not a lot there. But anyway, they split here too. Why? I'm not absolutely certain. But that's what they mean, local consistency. North part of Idaho, Pacific time, because they deal more with Washington folks. South part, they're over here on Mountain time. And the very eastern part of Oregon is on Mountain time, not on Pacific time. So there's all sorts of variations. That's what they mean, adjusted for local consistency. Now, no one here from India. I have had a couple of Indian students before. India is a pretty good-sized country, okay? And technically they should be, this part of India should be on one time zone and this part on the other time zone. Oh, sorry, this part on the other time zone. Not too much there. So what they do to keep the whole country in one time zone, split it on a half hour. Okay, so they are a little strange there, I think. I think they still do that. I'm not sure. And maybe with daylight saving time, they change half hour each way. I don't know. They do some sort of strange way there, just to keep the whole country on one time zone. Okay. If you can imagine how many time zones Russia has. We have 4, not counting Alaska and Hawaii. Russia, I don't know, at least 6 or 7. I mean, that covers a lot of territory. And they're way far north, so there's not too far between the time zones. Because you see, the 15 degrees here are there to there to there, you know, but daylight does change. Okay. Now, okay, sorry. Let's go back here. Daylight saving time. Clock set ahead in the spring ahead, fall back. Okay, for 1 extra hour of sunlight during the summer evenings. Now, some states, I think Arizona used to do this. They kept it the same. So in the wintertime, they were in mountain time. In the summertime, they were on Pacific time or something like that. I think they've changed now. But I believe at one time Indiana may have done something like that. But I think everybody changes now. But there have been times where people do it just that. All right. Now, if you have imagined what's going on here, remember that's 1 hour apart every 15 degrees, right? Well, something strange happens here. You can't all be on the same day. You're not, okay? Over here on that 180 degrees, there it is. It's called the International Dateline. And that's what the next slide is showing. Okay? International Dateline is the 180 degree meridian. Prime meridian over here in England, the 180 is smack dab in the middle of the Pacific, or somewhere in the middle of the Pacific. Now, it also is adjusted for local consistency. Here is the International Dateline. This is Alaska, which is part of the U.S., including the Aleutian Island chain. Okay? Hang on to that concept of an island chain. We'll talk about that in a few chapters. But Siberia comes really close here. That's part of Russia. Okay? And it comes really close. And the International Dateline goes right there. Part of Siberia is on our side, and part of the Aleutian Islands are on their side. So they adjust it for local consistency. They don't want this part of Siberia being on a different day from that part, okay? It's just a few miles away. They don't want them on a different day. Same thing with the Aleutian Islands. Same thing down here in the South Pacific. Here is New Zealand, but New Zealand also controls a few other islands around it, and so they jig it out here, and I can't think what group of islands are here, but they try to keep those in the same group as well. So there is a little variation there. I don't know if you want to hear a dumb story about the International Dateline, because remember, on one side of the dateline, it's one day, and on the other side, the other. But when I was in the Navy, for my first 3 years, I was in the Pacific. Were you ever in the Pacific? Ruben, never. You were, okay. And when you cross the Pacific, it just was so bizarre to me. When you cross the Pacific and pass a time zone, then you would either add an hour or lose an hour. And my goodness, we always added that hour during the dog watch. Did y'all have that? You know, that was a 2-hour watch around supper. One of those was a 3-hour and one was a 2. And when we lost the hour coming back the other way, or whichever way you're going, it was always during the mid-watch, which everybody on the mid-watch liked because they were only standing watch for 3 hours. Everybody else lost an hour's sleep that night. But when we crossed the International Dateline, my word, we always crossed in the middle of the week going one way, so we had an extra work day. But my goodness, coming the other way, it was always a Sunday, you know, that we lost. It seemed like, or a Saturday or Sunday. always seem to fall on the weekend, so we lost the holiday routine kind of day. Same thing with you?
Mm-hmm.
Yeah. Strange how that
On
works.
the way back, we set our clock back and just to
What's
local
that?
time. We just set the clock back to local time. And just that way we didn't have to change. We just moved
Yeah,
it back.
exactly.
Yeah.
Exactly. And, but anyway, I don't know if you heard the same dumb naval story. Don't know for sure if it's true. But obviously, or according to the story, there was some island in the Pacific who straddled the international date line. Okay? And on that date, in that island, this entrepreneur decided to build his bar straddling the international date line. So then on Sunday night on this side, this bar would close, but this one would still be Saturday night or Monday night or whatever. And then, so they just moved the people from one side of the bar to the other side of the bar, and he stayed open every day. Now, I don't know if that's true. That's a typical naval story. I don't know for sure if it's true. Because they couldn't serve on Sunday. All right, let's move to something more serious. Yearly time. Now, there's two types of years here. The star year is still sidereal. But now, rather than calling it a solar year, we call it a tropical year. Okay, now our tropical year is the interval between two consecutive spring equinoxes. And that's right around 365.24220, is that a precise number, mean solar days. Now, what does that decimal mean for you? What's it close to? A quarter, exactly. But not quite. Okay? Now, what do we do based on that? Say again? That was a really poor example of a
leap year.
leap year. Okay, finally you got it. Okay, good. Okay. What do we do every 4 years? We add a day because we've actually gone, our years are a quarter of a day too long, longer than this. So when we get to 4 years, you've almost added another day. Okay? So every 4 years we add a day. February 29th. And those are on years who's evenly divisible by 4. Is this a leap year?
No.
No. Okay. Is next year a leap year?
Yes.
Okay, yeah. 20 is divisible by 4. Okay. Now I'm guessing, if not during your lifetime, very close to your lifetime, definitely during my lifetime, we had a year that was divisible by 4 that we did not have a leap year. You want to know when that was? The year 2000. Y2K. Now, that wasn't what they were focusing on. But the reason is because this isn't quite a quarter of a day, is it? It's not quite. I mean, yeah. Not quite. Close, but not quite. So every century that's divisible by 4, and 2000, the 20th century, that was divisible by 4, on that, what would have been a leap year, they don't have a day. Okay. So once every 400 years, they don't do a leap year on that day, on that century. So the next 3 centuries, when they turn over, those will be leap years. But that fourth one, 2400, I won't be here. They will not have a leap year day that year. Okay? Now, let's get on here. Sidereal year. Sidereal means based on the stars, exactly. That's the interval between 2 consecutive alignments of the Earth and Sun relative to the stars. So let's say, I like the name, Betelgeuse is out there somewhere. When the Sun and Earth are lined up one way or another with Betelgeuse, and then the next time around when they are, that's a sidereal year. Okay? Spring equinoxes, though, we don't worry about the stars. That's just something to do with the celestial equator and the ecliptic. Okay? So those are not necessarily going to be the same. A sidereal year is about 20 minutes longer than a tropical year. And 20 minutes among how many minutes are in a year? That's not very much. So that's minuscule. Okay? Now, they mention here, and they don't say enough about it to make any sense at all, adjustment to keep calendar years current with the seasons are leap years. We just talked about that. But what in the world is a leap second? I mean, that makes no sense at all to me. So let's not even bother with that. I've already talked about what a leap year is. That's to make up for that almost quarter of a year, and to make up for the almost part of that on the every 4 centuries, we don't have a leap year. Okay. I want to call it a leap day in that year. Okay. Now, you had solar day and sidereal day. You had tropical year and sidereal year. When we go to monthly time, now we introduce our good old moon into the picture. But guess what? We have sidereal months based on stars. But what do we call the other one? The synodic month. Now, why in the world do we have to have 3 different names for the things that are not sidereal? I don't know, but we do. The sidereal month is the orbital time measured with respect to the stars, and that would be 27 1/3 days. Now, what do we mean by that? Okay? Here is how we measure a month. Not exactly, but close to it. Okay? When we have a full moon here, okay, the moon is facing the sun, and you get a full moon from Earth, okay? When you get up here, which is exactly 1 synodic month later, okay, I'm not sure they have this listed properly. This is a synodic month to here. That is the next full moon, okay? But you see, the moon isn't exactly positioned relative to the Earth the same. It has to get to be a full moon again, because here, that's not quite a full moon. It's a partial. It's a gibbous moon, okay? So you have to turn a little bit further. So that's the additional time required the same, and that's why the synodic month, see, this is the synodic month, this is the sidereal month. Because, you see, if you weren't looking at the sun and looking at the stars, that star way out there would be here, then it's way out there. That would be a sidereal month. 23 1/3 days, okay? Whereas the synodic month, which goes from phase to phase, that's 29 1/2 days. Now, any of our months 29 1/2 days long? Yeah. They're either 30 or 31, with 1 being 28 or 29 every 4 years, okay? So it's a little bizarre, but you see, we don't match it. It doesn't match up exactly, because we have to have the closest number of lunar cycles in a year is 12, but it's not exact. So some months, you'll have 2 events happening twice. I mean, 1 event happening twice, and other months, most of the time, it'll only happen once. Okay? For instance, full moons. If you had a full moon on September 1st, you'd probably have another full moon before the end of September, because they're 29 1/2 days across, so it could be. Especially those 31-day months, you definitely would have 2 full moons. We'll talk about what that is in a minute. Anyone know what that's called? Second? A blue moon, exactly. When you have 2 full moons in 1 month, the second one is called the blue moon. Okay? And that's why the expression is once in a blue moon, because they don't happen frequently. So they're almost always 1 month apart, except for those long months. When it happens to fall at the very beginning of 1 month, at the end of that month you have a second. Okay? Now, the synodic month includes the effect of revolving around the sun. See, not just do we revolve around the sun, which we do, but also the moon revolves around us. And the combination of those makes the synodic month little more than 2 days longer than the sidereal month. Okay. Anyone know easy ways to remember how many days are in which month? The knuckles, okay? When I was growing up, it was always the rhyme. 30 days, that's September, April, June, and November, all the rest of it, blah, blah, blah. But the knuckles I find much better. You make a fist, start with January here, January, a 31 day, February, shorter, 28, March, 31, April, 30, May, 31, June, 30, August, 31, no, July 31, then start over again, August 31. 2 31s in a row because you're starting off with the knuckle, and then September 30, October 31, November, December, and then December, January, about 31. So you see, you get more than one cycle of a moon in a month, okay, because most of our months are more than 29 and a half days, and it just doesn't work out evenly. But that's why months are based on lunar, moon. Okay. Which leads to segue into the moon. I'm sorry? Yes, let's do. The moon's a good place to take it. I was just going to say, there's a couple of examples here. How many time zones is Honolulu, Hawaii, away from New York City? You can look at the angles in your longitude, divide them by 15, and see about what they should be. So those are pretty easy examples. We just didn't do them. All right. 16.4 will be the moon. That's where we'll start when we get back. So I'm going to put this on.
Stop you at 3:15. Stop you at 3:15.
Yeah.
Or somebody to stop.
Yeah. 3:15 is when we stop and start the lab. Okay. And I meant to come back from my office, but I got to talk with somebody. I forgot to. The test is still down in the copy room, so I've got to go get it. So while y'all are working on the lab, I'll go get the test. I took it by earlier, but she was busy, so I'm sure it's ready by now. All right, let's look at our nearest neighbor, celestial neighbor, the moon. Okay? Only 380,000 kilometers away, which would be about 250,000 miles away. Okay? It's characterized by craters. What does that tell you? Second? It gets hit a lot. Why? No atmosphere. You're absolutely right. There it is. No atmosphere. Characterized by craters, which means it has very little or no atmosphere. And it has none. Okay? But it's made up of a variety of landforms, you might say. You have lunar highlands, okay? And you have what they call Maria. Now that came from the thing, when they first were looking at the moon, it looked like the darker areas there were rivers, marine environments. So they called them Maria, but now we know they were just ancient lava flows. We've been there. There's no rivers there, okay? There is no atmosphere there. And it was the subject of 12 Apollo missions. Some of them quite famous, as well as fairly infamous, okay? What was probably the worst Apollo mission? Second? 7? Is that the one? What happened to it? Okay, did that really happen? I didn't know that one. Okay, what I was thinking, and we'll get to this. Well, let's see if it's on the next slide. No, this is a picture of the moon, and it's really a composite of several pictures. But you see, there are crater spots all over it, just all speckled with that. But the darker areas are called the Maria. The lighter areas are called the highlands. Okay? Now, let's get a little more detail here, maybe. All right. Another ramification, result of being pummeled by meteors all the time, okay? That makes about 3 meters. Now, how much is 3 meters? I'm about 2 meters, so the ceiling is pretty close to 3 meters high. That is the thickness of fine gray dust on the surface. Not the best environment to play tennis or something, okay? Basketball, I wouldn't want to try, okay? Because you've got 3 meters thick of gray dust. It accumulated from these micrometeorite impacts, whereas either the big meteors, not the micro, burst rocks like crazy, or the micrometeor, all that dust is just constantly going. The glass beads form from the melted material because when these impacts hit, they're at enormously high speed, and the impact has a lot of kinetic energy to lose, and that produces a lot of heat, and that melts the materials, and then they're re-solidified as glass beads. Now, that's not just glass as we think of glass, but anything that melts and reforms. The rocks, mostly from the molten lava, are basalts, and we'll talk about that in the next chapter. But basically, we have 2 predominant types of rocks on the surface of the Earth. Most of the continental rocks are granite-based. Not all, but many of them are. The oceanic floor is made more of basalts, and that's what most of theirs. Now, anywhere you have active volcanoes, you're going to have lots of basalts. Their basalts come from volcanoes, not from the ocean floor. Okay, so, but the basalts come from, or formed from molten lava. Molten lava that is cooled quickly, we'll talk about that in the next chapter. Cool quickly means small, crystal size, very fine grained, and that's because of the quick cooling. Okay, so any volcanic activity near the surface, they cool quite quickly. Okay. The lighter colored highland rock, and that would be my guess, now they don't say it here, are basically from the siliceous silicates, just like our granites. The granites are typically lighter colored, the basalts are darker colored. So this is just like our continental rocks, the lighter colored highland rocks, and they were formed about 4 billion years ago. Now hang on to that number mentally for a while. The darker colored Maria rocks, those were the more of the basalts made from molten lava, they range from 3.1 to 3.8 billion years. Hang on to those numbers as well. Okay? Now, what's the internal structure? Now, this is pretty interesting. In fact, I find incredibly interesting. Okay? Now this is in kilometers, 65 to 130 kilometers of outer rock. Okay? 65, which would be about 40 miles up to 75 miles. Okay, 40 to 75 miles of the outer rock. The 40 is on the side closest to us. The 75 is on the back side, the far side. Now here's something bizarre about the moon, and it goes with that thing I just talked about. Here is the moon. When the moon is here, this is what you see. When the moon turns here, this is what you see. When the moon turns here, this is what you see. What are you seeing? Always the same side of the moon. Except for the astronauts that have been on the backside, no one has seen the backside of the moon. No one here on Earth, okay, except for those astronauts who've been around it. Because we only see one side. Which means when we spin, they're revolving. Okay? And the thickest part is back here, the thinnest part's here. That's why you can say the thickest part on the far side, because the far side's always back there. And the far side's one of my favorite convex strips. So that's beside the point. Okay. Now, they think there's a reason for that. Now, remember what other factor was so unusual about our moon?
Size.
The size. For our size planet, it's the biggest moon out there. It's not bigger than some of Jupiter's and Saturn's and some of the others, but for our size planet, it's huge. Now think about how many moons does Mercury have? None. How many does Venus have? None. Okay? Mars has 2, but they're little bitty moons. I bet you they came off the asteroid belt. Okay, but we have this huge moon. That doesn't sort of make sense. I mean, something's wrong with that picture. Here's what they think happened. Somewhere way back, this is the theory, in the early formation of the solar system, the sun may have been still exploding and doing things. Because remember the 4 billion years? That's a mere 1 billion years after the sun was formed, we think. We think it's about 5 billion years old. So maybe we were still sort of forming up as a solar system, Remember that hot, rocky stuff flying around up there? It hadn't really coagulated. They think it was probably a major collision with something. It broke off part of the moon, part of the Earth, and that became our moon. Okay? Because it's just like it's part of us. It spins with us. It does everything with us, and it's thickest on the backside. Interesting. Okay. 900 kilometers are partly molten iron core. Just about all the planets and moons, it seems like, have iron in the core. Okay? It's the densest material usually that's there in large amounts. And 900 kilometers is about 550 miles thick, partly molten iron core. Partly molten, meaning back when it was probably more molten, that's when you had the volcanic activity, the lava flow. But it has been cooling over time, so it's not only partly molten. We don't think there's any other moon volcanoes around now. It seems to have ended about 3.1 billion years ago, so don't seem to have come back. So this then pertains to the history of the moon. Those years I was telling about, here's where you draw them back. Recall. Okay. Stage 1, the origin stage. They think it was formed from material ejected from a collision with some enormous object with the Earth. Now, exactly where that was, about 4 billion years ago, 1 billion years after the sun basically got started. So it was still probably a very volatile time. Okay, things were flying around like crazy. I wondered if maybe that's when Venus got hit, okay, and made it start spinning backwards very slowly. But who knows? Lots of weird things were happening. Stage 2, molten surface stage. If it got hit by an object that big to break off, it's that far, 80 kilometers away. That was a pretty big hit. That took a lot of energy. It was probably molten at that time. It may have started molten, but it was. The surface was molten for about 100 kilometers down. That's about 60 miles down. And that was about 200 million years after the formation. 200 million years. From 4 billion to 3.8 billion is 200 million years. So that's where these numbers are kind of making sense. Okay? Now, they think a lot of that heating was from continual solar system debris impacts. I think when our solar system was early in the formation, there was lots of junk out there flying around, hitting things, bouncing, and that kept everything awfully hot. Okay? Stage 3, the molten interior stage. Finally, the surface began to cool, solidify, but the interior stayed molten. Now, they think a lot of that heat came from radioactive decay. The sun was formed by these, if you think back of our protostar becoming a star, it started with, after things got really, really hot, then fusion happened. And lots of radiation was thrown out. Lots of radiation was thrown out. And that's where the radioactive decay would have done. I think there were lots of it out there, and they, especially when the surface cooled, that was all trapped inside. Now, does anyone see a letter wrong here? They should be B's, not M's. Okay? This is billions of years. From the last slide and everything else we know, this is billions of years, not millions. What was the graphics person doing here? Okay? We'll make this billions of years, billions of years. Okay? Began, because think back here, 3.1 to 3.8 billion years, that's when the Maria from basaltic rock came from molten lava, volcanic activity, that's what they're talking about here. The molten interior stage that began about 3.8 billion years ago, ended about 3.1 billion years ago. That's when there were probably active volcanoes and lava flows. Okay. And you'll check in the book too, and I think you'll find those numbers are correct. Stage 3, those are billions in your book. So don't take the millions to heart. Okay? And, of course, down here it's also billion. Okay? Stage 4. Volcanic activity is pretty much quit. I think the core is now only partially molten. It's mostly solid. Hey, not much activity going on. And that's from 3.1 billion. Now, it's only 4 billion years old. It went through stage 1 in about 200 million years, stage 2, and then stage 3. And then for the last 3.1 billion years, it's been cold and quiet. Now, when you say quiet, I think they do every now and then record a moonquake. Just like we have earthquakes, they have moonquakes. There is still motion going on and stuff like that, but it's nothing nearly as bad as what it was early on. Lava flows and things like that. So, the surface is scarred by micrometeorites and meteorites. Why they threw this in here, I don't know, except before then the surface may have been not liquid enough, but sort of semi-liquid enough that you didn't get scarred as badly. You know, it would cover up the scars. Now it hasn't. So all those craters and things you saw happened in the last 3.1 billion years pretty much. Okay. Make sense? Yes. It is 315. Well, that maybe the Earth-Moon system would be a good place to start. That's 16.5. Good choice of time there, okay? So we'll begin 16.5 next time. That's Earth-Moon system. And you erase this. Now, and actually this Earth-Moon system is going to be more closely related to your lab next time than it is this time, whereas what we've been doing up till now is pretty closely related to the lab we're doing today. How did I figure it all? No, it just was luck. Okay. All right. So I'm going to pause this. Well, let's see. Let's get out of this. And get out of that. And get out of that. And get this out of here so I won't lose it. All right. Now I do have the labs up here. I don't have the test, but I do have the labs. So let me pass the labs out to you. I think I'll pause this for a moment until we get all set up and ready to go. Okay. Now they say here, I just turned on my recorder again. I turned off the screen so you can't tell whether it's on or not. Yeah, I said I just turned it They say you need to have done the previous lab first, and y'all have. Good for you. And is anyone here that did not get a copy of the previous lab? We did add one person since the last class that came in late and dropped out, I guess. So I may have to make extra copies of some things, but I think I got enough for here. This is talking a lot about what we just talked about today. What do we mean by noon? When the sun crosses your local meridian, that's called transits your local meridian. It's the highest the sun will ever be that day because it's lower than it before. When it reaches your local meridian, it's at the peak, and then it's going down after that. So that's actual noon. The daily event, the transit of the sun across your celestial meridian, defines your noon. That's not clock noon, but it is noon. Fundamental reference for the measurement of time. The interval from one noon to the next noon, that next transit, that's called a solar day. You're basing everything on the sun. When the sun crosses your meridian one day to the next day, that's one solar day. Okay. Now, if you've ever wondered where the initials come from, here we have it. When the sun was before your meridian, they called that ante, meaning before meridian. If you travel through places, especially over in Georgia, some in Alabama, I'm sure they talk about antebellum homes. Bellum, rebellion, that's the Civil War. The antebellum homes that survived were those ancient, really old homes that were before the war. Okay? Ante, A. So, before the meridian, ante-meridian, AM. Everything from midnight till noon is something AM, before the meridian. Whereas after the meridian, what do you call a note that you put at the end of a letter? Say again?
Post.
Postscript. Okay? Post meridian. What do we call the time after noon? After that meridian crossing? PM. 1 p.m., 2 p.m. Okay. Got it. Up until midnight. Okay. Now they do some stuff about how the Romans called their days. They had a strange thing. They said every day was 12 hours, so some hours were longer and some were shorter. That is a weird way to do business. But they use Roman numerals, so who cares? Okay. Part A, then, on page 370 of your lab, is solar versus sidereal day. Okay? Exactly what we were talking about in class today. So this is the lab for chapter 15. Some of this material was in the chapter today. Okay? Your solar day is based, as we said, on the sun crossing a meridian, whereas the sidereal day would be when some star crosses your local meridian, like maybe the North Star. When it transits your local meridian, day to day, night to night, that would be one sidereal day, not the same length. Okay? Now, here's why. And here we will pull up, turn back on this. Now, can y'all see this well enough with the lights on, or you won't put the light back off yet? Huh? Okay, I haven't tried it, so let's see. If it isn't, the light closest to the door, that's the switch to turn off if this doesn't show up well enough. Okay. Okay. All right, coming a little bit brighter now. Okay. The sun moves how many degrees? Okay, the sun doesn't move. How many degrees do we spin in a day? One time around? 360 degrees. Okay, I'm sorry. Okay, the sun is moving. Well, not really. around the ecliptic, it moves 360 degrees around the ecliptic, or appears to, in how many days? That's a year. 365 days. So it's almost 1 degree a day. Not quite, but awfully close to it. 1 degree a day. Okay? Now, therefore the sun is about 1 degree further from you when you have the next. Okay. If it's moving 1 degree a day, when the Earth moves that 1 degree, it has to spin just a little bit more to get to be your local noon that day, what we were talking about before. Okay? Calculate how long you will have to wait. Now, what they're referring to here, they sort of bounce all over the place here, and I don't bounce as well as they do. If you flip over one page to 372, okay, people at home can't see this, but hopefully you can get it. When the sun crosses, okay, to give a reference point there, let's start on vernal equinox, when the celestial equator crosses our ecliptic. So when the sun crosses our local celestial meridian, the ecliptic is right behind it, okay, and it's going to cross there. The next day, the sun is moved along the ecliptic 1 degree, okay? But our local celestial meridian, okay, if you were based on the stars, the sidereal day, that would be 1 sidereal day, but it's not. A solar day, it's moved 1 more degree, okay? Now that's the question. It says, referring to this, how long did it take us to turn a little bit further for us to catch the sun on our local meridian? Okay? That's what question 1 is about. Okay? The sun is about 1 degree east. Calculate how long you'll have to wait after that situation depicted on 1b so that the sun is along your meridian. In other words, your meridian has to turn just a little bit further, 1 degree more to get there. Okay? So, how long? Whoops, I'm in the wrong color. Okay. 1 spin of the Earth is how many degrees? 360 degrees. How many hours does that take us? 24 hours to go 360 degrees. Okay, so how many degrees is that per hour? 15 degrees per hour, right? Divide 24 into 360, you get 15. How many minutes are in the hour? That would be 15 degrees in how much? 60 minutes, right? So how many minutes would pass for it to move 1 degree? 15 into 60 would be 4. For 1 degree, that would take 4 minutes. And that's why, it'll come back, that's why 1 sidereal day is about 4 minutes shorter than 1 solar day. So that's what you need to do there. Express your answer in minutes. We just did. Okay?
So that right there is what
That's basically what you put for your answer to number 1. Okay? So we have described one way of showing a solar day is a little bit longer, about 4 minutes longer, than 1 sidereal day. Now, they refer you to figure 48.2, okay? And that's another way of describing it. When you're at noon on position A, 1 sidereal day later, you're at B, but now they don't have these divided up properly, but for you to spend just a little bit more to catch the sun at local noon, you have to spend just a little bit more, and that's 4 minutes later. So there's another way of looking at it. There's nothing to do there but just looking at it at a different perspective. Now, question 2 is really interesting. They refer you to figure 48.3, which is basically your zodiac. And how in the world they got any of these things to represent anything, I'm not sure. A few of them. Now, number 1, Cancer. How does that represent Cancer? I don't know. Gemini, which means the twins, that almost look like these two weird-looking shapes could be conjoined, so maybe they were twins, okay? Taurus, I sure can't make much of a bull out of that, but I guess these are long horns in front, and maybe those are 4 feet. I don't know. Aries, is that thing up there? I don't even know what an Aries is, and how can that be an Aries? I don't know. Pisces, does that look like a fish to you? I don't think so, but maybe you eat weird fish. I don't know. And this thing over here is an Aquarius, and Reuben was asking me how long an age of Aquarius was, and I have no idea, but I said it wrong. It's the moon is in the 7th house, which I think is probably Aquarius, the 7th constellation. That's the house. But Jupiter aligned with Mars. I was having to go back and do the song in my head. Jupiter aligned with Mars. And I don't know what the age of Aquarius was, but whatever that is, that's supposed to be an Aquarius. And then a Capricornus, okay. I think that's me, but I'm not even sure what a Capricorn is, you know. Not quite a unicorn, but I don't know. It's nothing to do with that. I don't know what a Sagittarius is. I think he's an archer, because that does look like maybe he's holding a bow and has an arrow back here.
It's supposed to be like Chiron, I think.
What's that?
It's supposed to be like a centaur.
A centaur?
Yeah, with like a bow.
With a bow. So, okay. He's got the bow. I don't see the centaur, but maybe he is, okay? And then a Scorpius. That, I guess, in some way looks like a scorpion. That probably comes the closest. I can't even remember what a Libra is, but I have no idea if it looks like that. What's that?
That's the scales.
The tail of what?
Scales, like scales.
Oh, scales. Oh, okay. Yeah, justice cycling scales. I guess maybe I could see that. Virgo. Okay, meaning virgin. I can't tell how you tell, but I'll take the word for it. Now, Leo, I would call a horse, but they call it a lion, so we'll go with the lion. Okay, we're back to Cancer. So there are your 12 zodiacal signs. Okay, that's what the figure shows. Now, I shouldn't have wasted that much time with it, because if you go back to question 2 on 371, it says that figure depicts the sun's apparent motion along the ecliptic where the zodiacal constellations are found in a heliocentric perspective. Okay, meaning sun's perspective. As the Earth orbits the sun, the line of sight of the sun toward the background stars also moves. Because when we are here, the sun is in Leo. And when we move over to here, the sun will be in Virgo, and then Libra, and on. So that's why the various houses here are the various things. So that's what it's talking about. Okay? Because this Earth is constantly moving around the sun, and that makes the background stars change over the period of a year. Okay, for example, the diagram shows the sun in Leo. A month later, it will have moved enough so Virgo lines behind the sun. Now, does anyone find a question there? I don't either. Okay, so question number 2 has no question, and I can't even imagine what question they could have been looking for. So, nothing to answer there. All right, move on to Part A. I thought we were just in Part A. Yeah, Part A over here on page 370 was the solar and sidereal day. Now we're in Part A, the analemma, so this must be Part B. Okay, the analemma, there was the word I was talking about, A-N-A-L-E-M-M-A. This is the details of the sun's motion, okay? And we can refer to the fictitious mean sun that moves uniformly across the celestial equator as on the meridian at noon and again precisely 24 hours later, blah, blah, blah. The real sun does not behave that way. Corrections to time are kept are not large, but they are there. they can be represented by that three-coordinate plot called the analemma. And this is Latin for the sundial. I don't know what gnomon is, or, that's the other word for the sundial. That's the one that actually does the shadow of the sun. So the analemma is a closed curve resembling a flat bottom figure 8 that you see on figure 48-4. That's your analemma. Okay? Now, it's a three-dimensional plot in two dimensions. Pretty interesting how they do this. Okay? Your horizontal scale actually has a couple of ways to look at it. These are degrees here. Don't worry about those at the bottom. The one at the top is times in minutes. And you see go from being 15 minutes on one side to 17 minutes on the other side. Not a lot of time difference there. Okay? Whereas on the vertical scale, that's the declination of the sun. What's declination of the sun? How far north or south it is from the celestial equator. So you see the equator is right there at 0. And you see it goes up to just about 23.5 degrees north down to 23.5 degrees south. Okay? So there is your tilt of the earth right here. Okay? And you see how that does affect time. Now, what happens in here, this is around the time when the Earth is farthest from the sun. Closest to the sun. We have a bigger variety of time because the Earth is moving quite rapidly. When we're farthest from the sun, around June and July, then we're moving more slowly, and that makes the top of the figure 8 be more narrow because we're moving more slowly. The days are much closer together there. The third dimension is then the day of the year. Now, it takes some effort to read this. You have to see which month is ahead or behind you to know which way to count. So this is October the 5th here. This is November the 5th down here. December 5th here. Just, you have to make sure you're going in the right direction. Okay? And your time, that's the top thing, clock noon, is right on the money on those days there. Okay. So there's your analemma, which is another word for sundial. And a lot of this talks about how it works. Okay? By the way, the equinoxes are when the sun is on the equator. There's near September the 22nd or 3rd maybe, and March the 21st it looks like. So you can find your equinoxes there, when the sun is crossing the equator. Okay. So there's lots of stuff here. And all the variations are referred to here. The tilt of the Earth, the elliptical orbit of the Earth, all that is taken into account. So if you flip over then to page 376, question 3 finally shows up. Briefly describe the effect on the shape of the analemma, that figure 8, if the ecliptic equator angle were to increase. It's now what? Ecliptic to equator angle. What's that? The tilt of the Earth? How far is it? Oh, yeah, I've answered it a couple times today. What is it? It's where Tropic of Cancer, Tropic of Capricorn. 23.5 degrees, okay? 23.5 degrees. What if that were to increase and go to 24 or 25 degrees? What would happen to the shape of your analemma? It would have to get longer. It would be stretched top to bottom, right? That would be greater. So that's what would happen if, so that's question number 3. Briefly describe the effect on the shape of the analemma if the ecliptic equator angle were to increase. The analemma would be stretched further. Okay? Obtain from your instructor the latitude of your location and fill it in below. Y'all remember this from last time? 33 degrees, 23 minutes, 45 seconds. Now that's pretty close to where we are here in Bessemer, Alabama. Okay? Now, with that in mind, determine the altitude over the southern horizon of the intersection of the celestial equator and your local celestial meridian. That's that picture we've been drawing before, so let's clear all this out of the way and draw our little globe here. Try to get in the middle. And here we are standing in Bessemer, Alabama. Okay, nice warm day. Actually, a wonderful August day, isn't it? I mean, this morning, I had the door open, it was cooler outside than inside. That doesn't happen much in August. Here is your horizon, and there, I don't have it quite in the middle, here is the celestial sphere, or half of it anyway. Now, we just said that our latitude of our location was about a third of the cut there, and this was the 33 degrees, 23 minutes, 45 seconds. Okay, so that means, what's that point directly overhead called? The Z word. Yeah, they used to make televisions. Oh, y'all don't remember that. Okay, zenith. Okay, and then the celestial equator would be about a third of that distance, and that is 33 degrees, 23 minutes, and 45 seconds. Okay, and what he's asking for here, determine the altitude over the southern horizon. Here's the southern horizon, here's the northern horizon. The altitude over the southern horizon of the intersection of your celestial equator with your local celestial meridian. Well, this is our local celestial meridian, that half circle. There is the celestial equator. This is the equator down here. So, what is the altitude of that celestial equator above our southern horizon? How would you get that? Anybody? Subtract from 90. Except I'm going to do 90. What will I do? 89 degrees, 59 minutes, and 60 seconds. Because 60 seconds is 1 minute, that would make 60 degrees, minutes, and 60 minutes would be 1 degree. So yeah, that's the same as 90. When you do the subtraction, what do you get? Pretty easy when you have those big numbers on top. What would that be? 56 degrees, 36 minutes, and 15 seconds. Perfect. Okay? So that goes on the line below that before you get to question 5. All right? Now, what we're going to do is use this analemma back on page 374, figure 48.4, and we're going to answer, and our answer up here in step 4, to fill in table 48.1. That's the one right here. And it was originally 47.1. I guess they changed, I don't know. But anyway, I put it at 8, so that's why it's written over that way. The latitude of Altegard, Norway, by the way, is +7. Okay? So what we need to do is find the declination of the sun on February the 15th. Now, does this picture tell you that? No. What does tell you that? The analemma. So what you have to do is find February the 15th. Anyone see where it is? right there on the right-hand side of the big part at the bottom, right? February 15th. And what are they asking for? The declination of the sun. Well, you read that on the far left scale, right? So go to your February 15th, follow that line all the way across there, and how many degrees north or south of the equator is it?
13.
Which way? South, 13 degrees south. You just use your analemma to determine that the declination of the sun on February 15th is 15 degrees south of the equator. 13. I've turned the page, I couldn't read. 13
Wait.
degrees.
It's on the 15th of February.
On the 15th of February, 13 degrees south. Right. I knew it was 15 degrees south. Okay? Let's go on and fill out all the declinations first. June 21st. What's the declination of the sun on that day? Say again? 23 and a half. That is summer solstice. We knew that one without even looking at this, didn't we? But you sure enough can find it, can't you? 23 and a half degrees north. Keep losing my page here, okay? October 15th. Declination of the sun is? Which way? South. Okay, very good. And December 22nd, say again?
So it was 8 south.
8 degrees south, right. And December 22nd? Yeah, 23 and a half degrees. Which way? South. Very good. Okay, with those in mind, y'all have them written down, so you call them out to me when I need them. What is the noon altitude of the sun at our location? Okay. Now, what is declination measured from? Or to? Or about? Yes, the celestial equator. And on February 22nd, what was the declination of the sun?
13 degrees south.
Say again?
13.
13 degrees south of the celestial equator. So that would be something about there.
Is that February 15th?
Yeah, February 15th. Was it that 13 degrees south?
Yeah.
Yeah. Okay, 13 degrees south of the celestial equator. Okay, so the sun is here. This is this. No, I drew a star. That's not the sun. Okay, it is a star, but it's not look like that. Whoa! I lost my line and everything. Okay. Here's the sun on noon on 15 February. Okay, 15 February. Now, what it's asking for is altitude of the sun. So that would be the distance above the southern horizon. What would that be? We know this distance was at 56, 36, 15, and this is below this, so this would be subtracted from this. Subtract 13 from there. And that gives you 43 degrees, 36 minutes, 15 seconds. There's your answer for the block of noon altitude of the sun at your location for February 15th. Okay? Let's go down to June 21st, and where's the sun then? 23 and a half north. So let's see, that was 33 here, so 23 and a half. Ooh, I didn't have it quite far enough. So let's just do this. Let's just say that's 21 June. Now that's 23 degrees, 30 minutes north of the celestial equator. Oh my goodness. You need a lab? All right, Chris is here.
That reminds me, I'm supposed to take another.
Yeah, and we just passed it, didn't we? So I was supposed to take a roll of a couple minutes ago. Luis is still here. Lexi is still here. Zarik is still here. Brianna hasn't made it in today, has she? I don't see her. Okay. Ethan is still here. I'm off one. I miss CJ. He's still here too. Ethan's still here. Amanda's still here. Jordan's still here. Gotcha. Jonah's still here. Patrick's still here. Maurice is still here. Derek hasn't made it in today, has he? Okay. Tegan is here. Chris just came in. Latricia is still back there somewhere. Okay. Heaven's still here. Ian's still here, mostly. Okay. Edward didn't make it in today, did he? I don't recall seeing him. Okay. Maya is here. Michael Pruitt is trying to do it remotely, so I'll have to hang on to him. Ken. Have I got that right? Ken is here, yeah. I'm having trouble reading your name because I read all of it. Diamond's still here. Maya came in. I forgot to mark you here. Okay, so I'm glad I called roll again. Okay, Ruben's still here, and Ryan is still mostly here. Okay, all right, so good deal. Now, we left off trying to figure out what the altitude of the sun was on June 21st from our location. Now remember, this one right here was 56 degrees, 36 minutes, and 15 seconds. That was the celestial horizon above the southern celestial equator, above the southern horizon. And the sun on June 21st is another 23 degrees and 30 minutes above that. So what do? Add, and that comes out. Now be careful here. The 15 seconds is easy, but what happens if you add 36 to 30? 66 minutes. Well, what's that? 1 degree and 6 minutes. So put the 6 minutes here, add a degree here, and what does that give us? You carry 1 degree. That will be 80. 80 degrees. Yeah, carrying a degree. Because 60 minutes is 1 degree. 60 minutes is 1 degree. So that 60 goes here and the 6 comes out here.
So
Okay.
it's 80, 6, and 15.
What's that? 80 degrees, 6 minutes, and 15 seconds. All right, that was on June 21st. Okay, I've lost my place here completely. Here we go. It's all Chris's fault. Okay, I gave away my thing I was working with. Okay. Now, October 15th. What was the declination of the sun? Second? 8 degrees south? Is that right? Is that what I heard? So now we're just 8 degrees south. So that's something maybe here. 8 degrees south. So we subtract 8 from the 56 degrees, 36 minutes, and 15 seconds. Subtract 8 from that, and what do we have? 8 degrees. Anybody? 48 degrees, 36 minutes, 15 seconds. Okay? And how about December 22nd? 23.5 degrees south of the celestial equator, and that would be about there. So you're 23 degrees, 30 minutes south of the celestial equator. So we take the 56 degrees, 36 minutes, 15 seconds, and subtract the 23 degrees, 30 minutes from that. What do you get? Anybody? Second? 33 degrees, 6 minutes, 15 seconds. All right. Now, what does that mean for us anyway? Let's take the extremes here. That means on June the 21st, the sun's up there, and that's 80 degrees. So we're almost 90 degrees. It's up there almost directly overhead, okay, on noon. But on December the 21st, we're down here at 33, barely a third of the way up in the sky. So no wonder it's colder. The sun is up, less direct radiation, and far less time being up in the sky.
So
Okay.
December is just not very hot.
That's what?
It's just not very hot.
No, exactly. Now we got to do all the same stuff for Altergard, Norway. Okay? The latitude of Altergard, Norway is 70 degrees. So, don't know what the easiest eraser would be. I'm going to try to erase all this and keep my celestial sphere. And I'm not sure that's the wisest move, but we're going to do it anyway. Watch me mess it up anyway. Oh, this is taking too long, but I'm going to do it. Okay.
Where's the latitude for Alfred?
The latitude was 70 degrees. Okay. I've got to draw that. That's why I want to get all this out of the way, because it's getting way too crowded. And that sun had way too many rays on it, didn't it? Okay. All right. Okay. Now, Altergard, Norway, 70 degrees is the latitude, meaning this is 70 degrees from the equator to our location, which means that is 70 degrees here. Okay? Yeah. So that means what is the this is celestial equator. So what is the distance above, or the angular distance above the southern horizon of the celestial equator? Say again? 20 degrees. Okay. All right. Now, declination of the sun on February the 15th. What was that? 13 degrees south. There it is. Here's your 13 degrees south of the celestial equator. That means what's the altitude of the sun on 15 February? I didn't draw it to scale. Sorry about that. What would be the altitude of the sun? Say again? No, okay. No. We're south of the celestial equator in February. It was 20 degrees, the celestial equator is 20 degrees above the southern horizon. And if the sun is 13 degrees below that, what's it's what? 7 degrees. 7 degrees is the noon altitude of the sun at Altergard. Look at that. Barely above the horizon, 7 degrees. No wonder it's cold there. I forgot to put the jacket on here. I should have. Okay. June 21st. Where's the sun? Declination of the sun? 23.5 degrees north of the celestial equator. This is 23 degrees 30 minutes north of the celestial equator. So what is the sun's altitude in Altergard? What would you do? Add it to 20, and what would that give you? 43 degrees 30 minutes, or 43.5 degrees. Not even halfway up the sky. On the high, the highest it'll ever be all year long. Not even halfway up. Okay? How about October 15th? It's what? 8 degrees south? Is that what you said? So 8 degrees south would be something like this. So this is 8 degrees south. So what would be the altitude of the sun that day? Say again? Yeah, 12 degrees. 12 degrees is the altitude of the sun. How about December 22nd? 23.5 degrees south. Well, here's the celestial equator. There's 20 degrees. 23.5 degrees would be somewhere down there. Where's the sun on that day? Below the horizon. It'll never rise. You won't ever see the sun on Altegard, Norway. It's above what circle? The Arctic Circle. So you will not see the sun on Altegard, Norway on December 22nd. It's below the horizon.
What do you want us to write?
I'm sorry?
What do you want us to write in that box? Just put below.
Well, however you want to do it. Noon altitude of the sun at Altegard, Norway. You can either say 3.5 degrees below the horizon. That doesn't really make, it never rises. It's fine. Okay, either one of those will be fine. All right. Now, here goes more erasures. Okay. Sort of a dumb, folkloric, historic question here coming up. Did anyone ever listen to Car Talk? Never mind. Okay. That's where I got folkloric and historic. Okay. No one even knows what Car Talk was, do you? Okay. It was a, huh?
Is it like podcast?
It was on public radio on Saturday mornings, I think 8 or 9 o'clock. These two guys from,
Is it like shop talk?
huh?
Is it like a shop talk kind of thing?
Yeah, they were mechanics, and they were funny. They were very Yankee, but they were as funny as you could imagine. And they knew everything about cars, but they kept laughing the whole time. It was really a good show. One of the brothers got Alzheimer's and died, so they took it off the air, but it was a great show. Okay. Here, this is number 6, is folkloric, historic. Rip Van Winkle awakens from his extended slumber and asks a passerby what year it is so he can determine how long he slept. The passerby quickly responds and then rapidly moves away. I wonder why. If he had been sleeping 70 years, it probably was pretty ripe and looked pretty rough, okay? I think I would have moved away pretty quickly too. I'm sorry, 20 years. 20 years. Realizing a 20-year snooze might be a world's record, he thinks he should pin down the date as well as the year. So he got the year. It's about 20 years, but he needs to know exactly how far. There may be some Russian out there that came close to it, so he wants to be sure he beats him, okay? He moves out from under the tree where he slept and measures the altitude of the sun when it crosses meridian. Clever guy. I happened to have a sextant with him, okay? I knew where his meridian was and all that kind of stuff. He finds that it is 44 degrees over the southern horizon. So that's where we'll begin this story, is that the sun, this is the sun now, at noon, is, I can't draw an arc very well, 44 degrees above the southern horizon. Okay? He knows that on the latitude of his chosen spot on the Hudson River in New York is 42 degrees. So now we can put this in here, and there's, got to sneeze, sorry. Yeah! Y'all awake yet? Okay, I want to make sure y'all are awake. Okay, 42 degrees, there's the equator. So now we do 42 degrees from here. This is 42 degrees. That's your celestial equator, right? So how far is the celestial equator above the southern horizon? Anybody? Not that hard. Second? How far is the celestial equator above the southern horizon if it's 42 degrees below your zenith? Second, 48 degrees? Perfect. Because they add to 90, right? So that's how far the celestial equator is above the southern horizon. Now, what does that combination tell you? If this is 48 degrees, the celestial equator is above the southern horizon, but the sun at noon is 44 degrees above the southern horizon. What does that tell you about the sun? What is the difference? The distance of the sun, angular distance of the sun from the celestial equator. What is that called? We've been using it. That was the first declination of the sun, exactly. So what would the declination of the sun be on this day he wakes up? Not that hard of math, is it? 4 degrees, absolutely. So the declination of the sun is 4 degrees south of the celestial equator, because you are south of it, right? Now that we know that, we can go back to our good old analemma and find 4 degrees south of the celestial equator, and you find 2 possible dates that he awoke. One on one side of that figure 8 and one on the other. What are those 2 possible dates? October 5th or March the what? I couldn't hear you. 10th, maybe 11th, something like that. March 10th, 11th, that's fine. Okay? So that's exactly what the question asked, on what 2 possible dates could Rep Van Winkle have awakened. Did y'all write those down?
So you can say it's 15th or 11th on March.
Yeah, you just choose whichever one you think is closer. I'll count either one of them right. Okay? Or the October 10th, looks like that's right. October 5th, wasn't it? Yeah, okay. All right. Now, he notices, clever guy that he is, that the buds are just appearing on this tree he slept under. So what date would that be? March. Okay. So mark that somehow that that's the actual date. Circle, that would be fine. I don't care. Make it so I know you understand. Now, as we saw previously, the analemma graphs the daily differences between clock noon and apparent noon when the sun crosses the meridian. As an example, check the analemma, and this one they really messed up. They said figure 4.3, I think it was, or 5 or something like that. And it's really 48.4, so they really had it botched up there. So check on that to see that on October 15th, find October 15th, pretty close to where we were. See it? Now go to the very top of the table, go up that line to the very top of the thing, and you see you're at how many minutes? 14 minutes. That's 14 minutes before clock noon. So anything to the left is before clock noon, anything to the right is after clock noon. So it happens to be the October, let's see. Okay, now, yeah, that was up there. That was just to give you a reference. Now let's go to table, and they bite system up again, I had 47.2, it's 48.2, sun time and clock time. So on January 10th, the sun crosses the meridian. Now all you answer in this first column, all you answer is before or after. Don't put a time in there. The first column is before or after. The second column, the far right column, you put how amount of time before or after clock noon. So January 10th, is that before or after clock noon? Okay, yeah, it's way over there. Okay, after. How much after?
8 minutes.
Okay, you said 8 minutes. What is that, January 10th? Yeah, go all the way to the top. Okay, I'll take your word for it. It looks like it may not be quite that far.
I think it's 7 minutes.
7 minutes. I think you're closer to 7 minutes. But I'll take either one of them. Okay. February 15th. First column, before or after? After. And how many minutes?
13.
February 15th. Looks like that's right at 14, doesn't it? I think that's right on the line. Okay. April 15th, tax day, our favorite. Oh, y'all don't pay taxes, do you? Okay. April 15th. Now this is where you're getting close in there. You got to figure out which one you are. What would you say? It's, the first thing is after. And how many minutes?
1 or 2.
Now, yeah. Get on the right one. That's the one that's going from upper left to lower right. And the 15 is right there. It's, I'd say, less than half a minute. Okay? Barely after, but less than half a minute. Less than 30 seconds. Okay? How about July 30th? Say again? After again. Boy, y'all are stuck on after, aren't you? July 30th. And how many minutes? Say again?
6.
Looks like it's pretty close to 6. I'll buy that. September 1st. Oh, we finally before? Yeah. How much before? Good. Fourth, third, second. In fact, I'm almost to say that's barely after also, but it's right on it. So you can say whatever you want to, right?
So which one? What do you?
That was September 1st. So September 5th is down there 1 minute after clock noon, right? Or before clock noon. But then count back your little ticks. That the white one then goes back to the 4th, the black one goes back to the 3rd, the next white one goes to the 2nd. So actually on the 1st, you're slightly before. I mean, slightly after, but it's only a number of seconds. So put whatever you want to there.
So what?
Second?
I see you know what you're right. I'm sorry.
Oh, okay. It was just a few seconds after clock noon. So I put after in the first column, a few seconds in the second column.
Was September 1st?
September 1st. Okay. How about October 30th?
Before.
Oh, we finally got it before, and it's well before. In fact, how much before? Isn't it 9?
16.
Say again?
16.
15 minutes before clock noon. Okay? Good deal.
4 and it's 15.
15 minutes before. Before in the first column, 15 minutes in the second column. All right. Number 8. Okay? Last page. Determine the altitude over the southern horizon of the actual sun and the time when it crosses your local meridian on the dates in the table below. Okay? So we got to go back to our local meridian. I wish I had left it on here and done this first and then done the others. But let's go back and change it. Somewhere here is my eraser. Okay. That last one didn't take a lot, so this won't take too much either. Okay. Anyone remember what our latitude was? 33 degrees, 23 minutes, 45 seconds. So we do this up here about 33 degrees, 23 minutes, 45 seconds. Now, does anyone happen to remember what that would have put our... And this, by the way, that line I just drew there is your celestial equator. Okay? So what would that put the angle of celestial equator over the southern horizon? We did it before. In fact, you wrote it down on page 376. You wrote both of these down. 56 degrees, 36 minutes, 15 seconds. All right. Now, it says determine the altitude over the southern horizon of the actual sun, as opposed to the virtual sun. Okay, no. And the time when it crosses your local meridian on the table, dates in the table listed below. Let's do May 15th first. Where do we go to find out your, where we would be then? What will help us know? The altitude above the southern horizon of the actual sun. May 15th. Anyone found May 15th yet? All right, what would be your, what are we looking for now? We're looking for both parts of it. First, go across horizontally to your vertical scale, and what do you get? 19 degrees where? North of the celestial equator. So another 19 degrees north here. I probably did too much there. 19 degrees north here. You add that to the 56, and what do you get? 75 degrees, 36 minutes, 15 seconds. Pretty far up there. May 15th? Pretty. So there's your altitude of the sun. While we've got that, May 15th, what time? The time when the sun crosses the meridian. On that date, in our, and this is the sun, on, what do we say, 15th of, was that the 15th of May? Yeah, 15th of May. What time does it cross? Four minutes before local noon, and what time would that be? 11:56. Which letters come there? AM. Perfect, perfect, perfect. Okay? Yes. Question? Someone said something. I'm sorry. Okay, May 15th? Okay, goes directly up from May 15th. And don't you hit 4 minutes on the nose? Do you see that? Okay. All right, June 15th. Let's first determine the declination of the sun on June 15th. Whoa, what would that be? 23 degrees. So 23 degrees would be just past the 19. So you add 23 degrees. This is on June, what was it, 15th? Okay, instead of adding 19 to it, let's add 23 to it. Oh, my eraser didn't work. And what would that give you? Pretty easy math.
33.
Second,
33.
are you adding?
Oh,
Because you're above the,
I was subtracting. Sorry.
what's that?
I was subtracting.
Okay. But you're above the celestial equator, so you add it, and how much? 79 degrees, 36 minutes, and 15 seconds. And let's see what the time it crosses the meridian. The 15th of June? Say again?
30 seconds.
I would say 12 noon. Because 15 is right on that. 0 minutes. So that would be 12 noon. I never know whether to put AM or PM there, so I put 12 noon. I write Noon, so I know. And on the other one, I write midnight, because I can't ever remember which one you're supposed to put with which. Okay, November 4th. Altitude of sun. We got to get the altitude of the sun first, but what do we need to get that? November 4th.
15 degrees.
Is what, 15 degrees which way?
South.
South. 15 degrees south of the celestial equator. So what do we do to determine the altitude of the sun? Since it's south, you subtract. 56 degrees, 36 minutes, 15 seconds. Subtract from that 15 degrees. And what does that give you? 41 degrees, 36 minutes, 15 seconds. Okay? What's that?
This is on November 4th.
I
This
can't
is the
hear.
November 4th one.
Yeah, this is November 4th. Okay? I just had it. There it is, November 4th. 15 degrees south. Okay? Now, what time does it cross the meridian?
So 11 to 44.
Looks like to me it's probably closer to 16 and some odd, but that's okay, whatever you want to call it. Before, so what time would that be? 11, yeah, 40, 44, 45, something like that, yeah. All right. Got it? Christmas Day, December 21st. Okay, I know y'all wake up and think, where is the sun crossing the celestial? No, whatever you think. What would be the declination of the sun on Christmas Day?
24 degrees.
I don't think it's ever 24, is it?
No, it's not quite.
I say 23.
23.
Yeah, I would argue maybe even closer to 23 and a half. It's awfully close. It's flat. Remember that? It's flat down there? So it's almost the same. So let's say 23 and a half degrees south of the celestial equator. So somewhere like this, it's 23 degrees, 30 minutes south of the celestial equator. So this is going to be pretty easy to do. Oh, I don't have to, here's the only thing I have to do. Oh, yeah. All right. You're subtracting this time 23 degrees, 30 minutes. And what will that be?
33.
Second, 33 degrees, 6 minutes, and 15 seconds. Okay? So there's the sun on Christmas Day, and that's what you always wonder. How's the sun going to get today? That's what you ask on Christmas Day, right? Always bug my parents about that. Yeah, right. Okay? And what time will it cross the meridian that day? Second?
At 12.
At 12. Maybe 11:59:43 or something like that. That's awfully close to 12. Okay, I would leave it 12. Good deal. Not quite as long as the last lab, is it? I'd say right at noon, 12 noon. Are there any questions? Is this making sense? Or killing time? Not killing time, okay. Adjusting time, okay. All right. All right. Are there any questions? Anything I can do? None? Okay. Because at the last break, I forgot to go by the, what you call it? Copy room. I've got to go down to the copy room. So y'all want to take another little break while you're getting your formula and equation sheets together and typing them out in very small type? Okay, yeah, I thought so. Okay. You got your magnifying glass? Okay. Okay. All right. All right, for me to erase this one, you want it left up there a little longer. Anybody? Anyone need it a little longer? You do? If you're finished with it and want to turn it in, I'll take it. Give me something else to put in the pile that I haven't graded yet. Okay.
And you want section on there? Or you want,
What's that?
you want the class section on there? Or
No, I don't know what they can put that.
Okay, so they're about to take the test early?
Oh, no, we can't do that, can we?
Yes. If they are, I'm going to back up.
Yeah. Unless there are questions, why don't y'all take a little break while I run down and get the copies. All right, I'm going to be waiting forever this weekend in the night.
Did we have a question?
Yeah.
There's a question about the first slide.
Okay.
Everybody's turned theirs in, so we can't help. Nobody can help us.
Oh, okay. What's that?
The nuclear bomb on the moon.
Have you heard about that?
No,
I hadn't either. Okay. All right. You showed that was theta, and I take it that's alpha. Okay, you understand why that's alpha? Because it's the same as that, right? And then these two add to 90. These two add to 90, so that's why it's theta. Or that leave that as a alpha. Yeah, fine.
So it's right?
That's perfectly fine. I understand it.
You didn't need us to write anything specific
No,
on it.
that's fine. If you understand it, that was it. Huh? Okay. All right, good deal. Okay. I'm going to end this.